The astonishing endurance of Voyager 1 can be credited primarily to its unique energy system. Spacecraft that utilize solar arrays which only function optimally near the Sun. Voyager relies on three distinct devices known as radioisotope thermoelectric generators, RTGs. These specialized power units operate by converting thermal energy produced through the radioactive breakdown of plutonium-238 into electrical power. At the time of its departure from Earth in 1977, these RTGs were generating approximately 470 watts, sufficient to power multiple standard light bulbs. However, by the year 2023, that energy output had dropped significantly, nearly cut in half, with the spacecraft losing about 4 watts each year. As the available energy to wane, those managing the mission are confronted with difficult decisions concerning which instruments and functions are essential and which can no longer be sustained. This situation mirrors a medical triage, where choices must be made about which systems must remain online to achieve mission objectives and which ones must be turned off. A notable decision occurred back in 2011, when engineers chose to shut down the heater that kept the ultraviolet spectrometer warm. Surprisingly, the instrument kept functioning despite being exposed to a bone-chilling temperature of 110 degrees Fahrenheit, minus 79 degrees Celsius, far colder than it was ever intended to endure. Inside the Jet Propulsion Laboratory's control room, where the Voyager project is still actively managed, past and present converge. Sleek modern digital monitors sit alongside archaic equipment from decades ago, all still serving vital roles in maintaining communication with the distant craft. Some of the personnel on the current team were not even born when Voyager first launched, while others have devoted the majority of their careers to overseeing the probe. Many compare their duties to looking after a beloved yet increasingly fragile elder, marveling at its resilience while acknowledging its vulnerability. Voyager 1 must perform a rotation maneuver twice each year to ensure its high-gain antenna remains correctly oriented toward Earth. These maneuvers require the consumption of hydrazine, a finite and irreplaceable propellant. Estimates suggest that the remaining fuel will be sufficient to allow orientation adjustments until around the year 2040, although dwindling electrical power will likely bring the mission. To prolong the spacecraft's operational lifespan, engineers have devised clever software modifications transmitted across vast interstellar distances. These updates minimize the frequency with which the thrusters are required to fire. The Deep Space Network, an array of enormous radio antennas located in California, Spain, and Australia, allocates daily observation time to intercept Voyager's extremely faint signals. These signals, which have traveled for over 21 hours at light speed, barely rise above the cosmic background noise. Advanced digital filtering and signal processing techniques are employed to extract meaningful data. With a data transmission rate of just 160 bits per second, infinitesimal compared to modern internet speeds, Voyager 1 still manages to gather and send home invaluable scientific information. Its cosmic ray detector captures high-energy particles originating from beyond our solar system, while the plasma wave sensor measures electron densities in the interstellar environment. Meanwhile, the onboard magnetometer detects magnetic fields that exist in the vast spaces between stars. The collective data gathered by these tools provides an unprecedented glimpse into an otherwise inaccessible region, the enormous, invisible medium through which our solar system journeys as it orbits the Milky Way. Projections suggest that Voyager will be able to continue transmitting useful data until sometime between 2025 and 2030. Beyond that, the available power will be insufficient to keep both the instruments and communication systems running. More than 4 decades after its launch, and well beyond the tenure of its original development team, Voyager 1 began sending back data that diverged sharply from expectations. Embedded within its routine telemetry was a peculiar and subtle auditory signature, a soft, rhythmic pulse at a low frequency, completely unlike anything previously recorded by the plasma wave instrument. This mysterious hum was restricted to a narrow frequency band and exhibited an oddly consistent pulsing pattern. Initially detected during a standard scan of the interstellar electron density, mission engineers were quick to suspect that the anomaly might be a glitch. After all, the probe was functioning far beyond its intended service life, using electronics built in the 1970s. Comprehensive diagnostic tests were conducted and data from various other onboard sensors were meticulously analyzed. Still, the peculiar hum persisted and was registered by multiple receivers within NASA's Deep Space Network. Suddenly, what had seemed like a routine procedure became a matter of urgent investigation. Veteran team members noted that this unusual pattern didn't match any recognized astrophysical phenomenon, solar fluctuation, or equipment-related malfunction. Its persistent and structured quality with precise repetition suggested one of two possibilities: either a natural occurrence that had not yet been identified, or something potentially crafted with intent. The signal's mathematical regularity sparked comparisons to the earliest pulsar detections, which were initially jokingly considered signals from alien civilizations before being confirmed as emissions from rapidly spinning neutron stars. NASA rapidly formed an expert panel comprising radio astronomers, plasma physicists, and data scientists. The team compared the observed hum against extensive databases of known cosmic signals from pulsars and magnetars to emissions from active galactic nuclei. No existing records matched the strange sound. Even more baffling, the anomaly was not a fleeting event. It consistently, which effectively ruled out transient cosmic occurrences like supernovae or gamma-ray emissions. Voyager had stumbled upon something entirely unprecedented, something no one had anticipated during its design or launch. The eerie nature of the discovery was hard to ignore. It was as if one heard a deliberate knock in a room that should have been empty. Humanity's furthest traveling spacecraft had crossed into an enigma. Shortly after this unusual signal was identified, another equally puzzling event was recorded in the spacecraft's telemetry. Voyager 1 had unexpectedly altered its orientation. This subtle reorientation had occurred without any instruction from Earth. Logs revealed thruster firings, yet no commands had been transmitted by mission control. Initially, the team examined the possibility that a buried software routine, perhaps a safety protocol from decades ago, might have been triggered automatically. Redundant systems and fail-safes designed to activate during crises were thoroughly reviewed. However, none could explain the precise maneuver that was executed. The thruster activity was not arbitrary either. It followed a calculated sequence that shifted the probe's aim in a deliberate and directed way. Even more curious was the new direction in which Voyager was now pointed. Its long-deactivated camera platform had been turned to face an otherwise insignificant portion of the sky, devoid of prominent stars, galaxies, or known celestial bodies. The proximity and timing between the appearance of the mysterious hum and this orientation shift raised suspicions that the two might be related. Statistically, it seemed implausible that such anomalies could occur independently. At NASA's Control Center, analysts worked tirelessly, digging through years of trajectory data, system logs, and previous signals in exhaustive detail. The tension in the room was palpable. After ruling out all conventional causes, it became apparent that the orientation change was not an error or momentary deviation. It was real, consistent, and sustained. Whatever had triggered the maneuver had effectively altered Voyager's path through space. As further scrutiny was applied to both the hum and the course correction, researchers discovered a new irregularity embedded in Voyager's radio transmissions: extremely faint shifts in frequency and timing. These alterations, once examined, formed repeating structures. They weren't random, nor did they appear to be caused by interference from the interstellar medium. When charted visually, the patterns resembled geometric shapes and recursive sequences, some looking like echoes of Voyager's own communication style, as though something were reflecting or mimicking its signal. The anomalies remained consistent across different transmissions and were not one-off artifacts. NASA enlisted codebreakers and artificial intelligence specialists to analyze the pattern using advanced machine learning models and cryptographic algorithms. The results were nothing short of stunning. Segments of the detected pattern showed similarities to components of the Arecibo message, an intentional radio transmission humanity had sent into space in 1974.